Okay, our problem is 664. The axle of the freight car is subjected to a wheel loading of 90 kilonewtons. If it is supported by two journal bearings at C and D, determine the maximum bending stress developed at the center of the axle, where the diameter is 140 millimeters. So we have an axle. It has two wheels. Each carries 90 kilonewtons of load. We have two bearings at points C and D, and the distance between the bearing and the wheel is 250 millimeters. The system is symmetric, as you see from the figure, and the distance between two wheels is given as 1500 millimeters, so 1.5 meters. Okay, so let's draw the free body diagram first. In fact, we have two wheels. Each carries a load of 90 kilonewtons. Let's say that these forces are F. Then we have the reaction forces at point C and at point D. I choose the direction of the reaction forces downwards in the vertical direction. We don't have any horizontal component of the force in the system, of course. So if we write the static equilibrium, certainly we will see that Fc is equal to Fd, and that will be equal to 90 kilonewtons. That's okay. Now let us define the variables first. So let's say that L1 is 250 millimeters and L2 is 1500 millimeters. Okay. Now what we are going to do is we will draw the first we need to determine the bending moment distribution through the shaft. Okay, through the axle. You can choose either side. Either you can begin from C or begin from D. Of course, I begin from C. I put my origin, my reference point to the point C. Therefore, I will make the first cut between C and A. So in this region I have the FC, I have the bending moment M1 at the cross section. I choose the bending moment in a manner that it will be the Z coordinate is out of the screen towards us. In fact, according to right hand rule, this gives us the moment in this direction. Now if you write the static equilibrium, certainly you will find that M1 is equal to minus Fc multiplied by x1, if you say that x1 is the coordinate beginning from C. Okay, now next we will cut the structure between A and B, so from here. Now I have the reaction force Fc, then force acting on the wheels, then the bending moment in this region. Now, of course, Fc is, so this distance is x1. Again, I made an arbitrary cut. So the moment generated by this force is minus Fc multiplied by x1. Since this distance from C to A is L1, the distance to the cut is x1 minus L. Therefore, moment generated by the force F is F multiplied by x1 minus L1. Okay, now I will make the last cut. It will be between point B and D. Now I have Fc, I have F, second F coming from the second wheel. Certainly I will write the moment M3 in this region. So it is moment generated by Fc is minus Fc x1, since it is in the same direction with the M3. Certainly the sum has to be equal to 0. Again, I write the static equilibrium for this element. Then I have the moment of this force, the wheel at point A, that is F multiplied by x1 minus L1. Okay, now then the moment generated by the F, so force multiplied by this distance is x1 minus L1 minus L2. Okay, now I have the moment distribution. If you draw the moment distribution, this is what you are going to see. So basically the moment linearly increases in the first region. Since I have minus sign and Fc is 90 kilonewtons, moment is minus 22.5 kilonewton meters. It is negative and it increases linearly up to the first value. Then it will be constant for this region. Finally, in the last part, it will go to 0. Okay, we are asked for the stress at the center of the axle. So at the center of the axle, moment is minus 22.5 kilonewton meters. I'm just looking at the absolute value, therefore I omit, since it is a circular shaft, the geometry is symmetric, therefore the compressive stress, I see the maximum stress on the surface of the axle. In fact, maximum compressive stress is equal to the maximum tensile stress. Therefore I will omit the sign. So m multiplied by the radius divided by the bending moment of inertia will give me the maximum stress. In fact, bending moment of inertia for a circle is P r to the power 4 divided by 4, where r is the diameter. If you put the values for r is 70 millimeters, so 70 multiplied by 10 to the power minus 3, 7 10 to the power minus 2, and from here you can calculate the bending moment of inertia. Moment is 22.5 kilonewton meters, so 22.5 10 to the power 3, and the radius is again 7 10 to the power minus 2. Okay, our problem is 667. The shaft is supported by smooth journal bearings at A and B that only exert vertical reactions on the shaft. If D is equal to 90 millimeters, the diameter, determine the absolute maximum bending stress in the beam and sketch the stress distribution acting over the cross section. Okay, now we have a shaft and we have a distributed load which has a magnitude of maximum magnitude of 12 kilonewton meters. It is uniform between A and B, and it uniformly increases from 0 to 12 kilonewton per meter from the free end to the point B. We have two bearings at A and B. They exert only vertical forces, so there is no horizontal force, and the cross section is circular. The diameter D is given as 90 millimeters. And next we have the distances. So from A to B is given as 3 meters, and from B to free end is given as 1.5 meters. Okay, first thing that we are going to do is to define the variables. First, let me draw the free body diagram of the system, in fact. And let us define the variables. I have a beam. We have two shafts at point A and B. So this is FA, and then we have a force acting at point B. This is FB. There is a uniformly increasing distributed load. Magnitude is W. And we will define the distances. So from A to B it is L1, and from B to free end it is L2. It is circular. The diameter is 90 millimeters, so radius is given as 45 millimeters. L1 is equal to 3 meters and L2 is equal to 1.5 meters. Next we have the W. W is equal to 12 kilonewton per meters. Okay, first thing that we need to do is to determine the forces FA and FB. So we will write static equilibrium for this. Sum of the forces has to be equal to 0. From here, FA plus FB, the resultant force of this uniform distributed force is W L1. It is in the opposite direction. Then I have the resultant force of this uniformly decreasing part. This is minus W L2 divided by 2, and this is equal to 0. Now second, I will calculate the moments. In fact, so sum of the moments acting on the system has to be equal to 0 with respect to any point. In fact, it seems to be rather logical to put my origin of coordinate to the right hand side of the beam, X. So therefore I can write the moments generated. I assume that clockwise direction is positive for the moments. So FA multiplied by L1 plus L2, then FB multiplied by L2. Now I will calculate the moment generated by the uniform force. So first this part, so it is minus W multiplied by X. So X is the arbitrary location in this region, and it begins from L2 to L1 plus L2. So from here to here, dx. This is the moment generated by this uniform part, minus 0 to L2 now for this part, force is changing with respect to X, so it is Wx divided by L2. Okay, so according to X, and multiplied by dx, and this has to be equal to 0. Now let me calculate the integrals. Fa multiplied by L1 plus L2 plus Fb L2, Wx is equal to Wx square divided by 2. I continue below, plus integral of this equation. So by the way, it has bounds from L2 to L1 plus L2 plus minus, we have negative sign here, minus W L2, we have x square, x cube divided by three, and this is from 0 to L2. And this is equal to 0. So let me write the whole expression here in order to make it much more clear for you. So this is Fa L1 plus L2 plus Fb L2 minus W x square divided by 2 from L2 to L1 plus L2 minus W divided by L2 x cube divided by 3 from 0 to L2, and this is equal to 0. Okay, so these are our equations. Okay, so if we write the if we put the variables into its places, what we are going to get for the moment is moment equilibrium is Fa multiplied by L1 plus L2 plus Fp multiplied by L2 minus W divided by 2 multiplied by L1 square plus 2L1 L2 minus WL2 square divided by 3, and that's equal to 0. From these two equations, from the force equilibrium and moment equilibrium, we can calculate the reaction forces FA and FB. So FA is equal to WL1 divided by 2 minus WL2 square divided by 6L1. If you put the values, what you're going to obtain is 16,500 newtons. And for FB, it is 3L1 square plus 3L1 L2 plus L2 square multiplied by W divided by 6L1. Then the value that you are going to find is 28,500 newtons. So these are the reaction forces at the supports. Now let's draw the moment distribution. In order to draw the moment distribution or internal bending moments, first we will cut the structure between the free end and point B. So we will make the first cut from here and second cut between B and A. So remember that we put the origin to X. Okay. So I will make the first cut. I have M1 here. My reference is here, and the value here is Wx divided by L2. So this distance is X, in fact. Now from here you can find the M1. M1 is equal to, here the resultant force is Wx divided by L2 multiplied by X divided by 2. This is the resultant force multiplied by, I know that the resultant force of this distributed load will act at the centroid or center of gravity of centroid of this area, that is X divided by 3. So M1 is equal to minus W X cube divided by 6L2. Okay, so this is the result for the first part. Now I will make the second cut between B and A. I have M2. I have the uniformly distributed load up to B. So remember that I take the moment with respect to the cut. Okay, I will do the same thing here. So sum of the moments has to be equal to 0. From here I can calculate the M2. M2 is equal to minus, this distance is L2. First I will calculate the moment of this area, minus W, it is x minus L2, and then I know that it is at the center, so it is at x minus L2 divided by 2 plus x minus L2 divided by 2. So because this is the resultant force of this uniform distributed load, so this is square divided by 2. Minus, now I will calculate the moment of this area. Now here the resultant force is W L2 divided by 2, and this distance is 2L2 divided by 3. Therefore it is, the load arm is x minus two L2 divided by 3. So these are my moment distributions. Okay. Now let's draw the moment distribution. So this is my x now, this is my moment, now in the first part M1 is increasing in a cubic manner. Okay, so from 0 to L2, and when it is L2 it makes a peak and it's negative. So it is up to B, so let's say that this is point B, it goes like this. Oh, we made a mistake. Sorry. For the point B also we have the FB. I forgot to take the moment of FB. So the moment of FB is equal to plus FB multiplied by x minus L2. So we have the moment of this force here. I forgot to take the moment of this force. Okay, now this is the moment in the first part. Then in the second part, moment increases, and as you see from the equation, it's parabolic, and in fact it goes up, and it becomes zero when at the point A, since there is no moment coming from the support. So this value is minus 5,000. And it passes to 0, and it reaches to another value here. Now the point is, which one is the maximum and what is the maximum value in the second part? So this is m1, m1x, and this is m2x. In order to find the maximum, what we are going to do is we will take the derivative of m2 with respect to x, and make it equal to 0. Okay. Then from here we will find the extremum points. So maximum and we will find the x maximum from here as 3.125 meters away from the free end. Okay, this is the point where the moment is maximum, and in fact maximum moment is then m2 x maximum, and this gives us 11,343.8 Newton meters. Now this value is greater than minus 5,000, therefore the maximum stress occurs at the point where we see the maximum bending moment. Okay, now let's calculate the bending moment of inertia. Bending moment of inertia for a circular cross section is P r to the power 4 divided by 4. If you put the values, r is 45 millimeters, it is going to be 3.22 10 to the power minus 6 meter to the power 4. Now we can calculate the maximum bending moment. since maximum stress, it is m2 x max multiplied by the radius divided by the bending moment of inertia. So let's put the values. This is 11,343.8. R is equal to 45 10 to the power minus 3 divided by 3.22 10 to the power minus 6, and from here maximum stress can be calculated as 158.5 megapascals. Now it is also asked us the stress distribution at this point. In fact, if this is our axis of symmetry, stress distribution at the top of the beam, it will be compressive because we have a positive bending there. And it will be symmetric, and we will have tension at the bottom and compression at the upper part. This is minus 158.5 megapascals, and this is 158.5 megapascals tension, since this is the cross section. Of the shaft. Okay, our question is 672. Determine the absolute maximum bending stress in the 40 mm diameter shaft which is subjected to the concentrated forces. The sleeve bearings at A and B support only vertical forces. Okay, so we have a shaft and we have vertical forces, one concentrated force of 1800 newtons and the other one is at the free end, so it has a magnitude of 1350 newtons. We have two bearings. These bearings only resist to vertical forces, therefore there is no force in the transverse direction or in the lateral direction, let's say, and in fact there is no reaction moment coming from bearings A and B. Okay, first thing that we are going to do is to define the variables. Let's say that this 300 millimeters distance from A to the concentrated force as L1. Then we define 450 millimeters from this concentrated force to bearing B as L2. Then L3 will be from bearing B to the free end, which is 375 millimeters. Okay, diameter is given as 40 millimeters, and let's say that this 1800 Newton load is F1 and 1350 Newton of load is F2. So F1 is 1800 and F2 is 1350. So first thing is to find the support reactions. This is the free body diagram of the shaft. So we have FA and FB. We don't know the direction, we are going to calculate it. In fact, we will write two equilibrium conditions. Sum of the forces with respect to sum of the moments has to be equal to 0. In fact, it is better to calculate the moment with respect to point A. This will eliminate the contribution of point A since it will not generate any moment. Therefore, I can easily calculate the magnitude of the force Fb. So this is F1 multiplied by L1 and F2 multiplied by L1 plus L2 plus L3 divided by Fb multiplied by L1 plus L2, because moment generated by Fb has to be equal to the sum of the moments generated by F1 and F2. Therefore, from here I can calculate the Fb. In fact, I don't need to calculate the Fa. This is sufficient for me to determine the bending moment distribution. I will put my reference point to the right hand side where F2 is acting on. So I will begin to cut the structure from the left hand side. First I will cut the structure between B and F2, so from here, and in fact then I will find M1 as minus F2 multiplied by X. Second cut will be made between F1 and Fb here. So as a result, I will have M2. So I will calculate the moment with respect to the cut always. So this will eliminate the shear force at the interface. Therefore, I don't need to write the contribution of the shear force to the moment. So if I take the moment with respect to the cut and saying that sum of the moment is equal to 0, M2 will be equal to minus F2 multiplied by X, because F2 and M2 will try to rotate this piece in the same direction, plus Fb X minus L3, because from B to F2 it is L3, therefore the moment arm is X minus L3. Okay, so this is M2. Finally, I will make the last cut between point A and force F1. Therefore, M3 is equal to moment generated by F2. So this is minus F2 multiplied by X. Then I have the contribution of Fb, that is Fb multiplied by X minus L3, because it will try to balance the M3. And finally, F1, again it is negative, minus F1 X minus L2 minus L3. So this distance is X minus L2 minus L3. So these are the moments that I have. In fact, if you draw the moment distribution, bending moment distribution through the beam from the free end to the point B, it is minus 506.25. Then it will tend to increase up to point A. Then it will reach the value of 121.5 at A. Then it will go to 0 at sorry, this is where the point just a moment. So this is the 1 and here it is A. Okay, so this is the moment distribution, and we are asked for the maximum bending stress, the absolute value of the maximum bending stress. In fact, we will see the maximum bending stress at the point where we have the maximum bending moment, and this is the point B. In fact, then next thing is to calculate the bending moment of inertia. Bending moment of inertia for a circle is p r to the power 4 divided by 4. So fourth power of the radius, r is the radius here. Then from here you can easily calculate the maximum value of the bending moment. So the maximum bending moment is 506.25. Radius is certainly 210 to the power minus 2, and then you will divide it by the bending moment of inertia and you obtain the result. Okay, our problem is 688. If the beam has a square cross section of 225 millimeters on each side, determine the absolute maximum bending stress in the beam. Now, we have a beam as seen in the figure from A to B. It is fixed to the wall at point A. We have a distributed load of 15 kilonewton per meters acting on the beam beginning from A and on a length with a length of 2.5 meters. Then we have 6 kilonewtons of point load acting at point B. So well, first thing that we need to do is to draw the free body diagram of the system. But before that, let us define the variables, or let's draw the free body diagram of the system first. So okay, so this is our beam. Let me change the pen. And this is point B, this is point A. We have a distributed load with a magnitude of W, and then we have a point load here. Let's say that this is F1. It has a magnitude of 6 kilonewtons and W is equal to 15 kilonewtons per meter. We have the length L, and this is 2.5 meters. Now we don't have any horizontal force, we only have vertical force component. Therefore on the wall at point A we have a support reaction Fa, and certainly we have bending moment or reaction moment Fa. So this is our free body diagram. In fact, we have a square cross section. This is the cross section of the beam, and let's say that the edge length is A, and A is equal to 0.225 meters. Okay, so this is the problem that we have. We are asked for the absolute maximum bending stress. Therefore, we need to determine the point at which, or we need to determine the point on which the bending moment is maximum. So we need to draw the moment diagram first. In fact, I can begin by calculating the support reactions, because I can cut the structure either from the left or from the right hand side. But in fact, in order to avoid the calculation of the support reactions, I put my reference point to the right hand side, and I begin to cut the structure from right hand side. So let's make the cuts. So first I will cut the structure from here, so somewhere between the distributed load and point load. This will be my first cut. So this is my F1. I have the shear force. Let's say that this is V, and I have bending moment. Let's say that this is M1. So sum of the forces has to be equal to 0, and bear in mind that this is my reference point X. So V has to be equal to minus F1 in this case, and M1 has to be calculated. I take the moment with respect to the cut. This distance is X, therefore let's say that this is V1, by the way. M1 is equal to then minus F1 multiplied by dx. So this is the moment M1. Okay, so this is my first cut. Now I will make the second cut. I will make the second cut between A and the beginning of this distributed load. So I will draw it here. I have the distributed load. I have the point load F1. I have the bending moment M2, and I have the shear force V2. I will not calculate the V2 for this problem. In fact, I can. Or let's do it. No problem about that. So V2 is equal to minus F1 minus W. This length is X minus L. So this is the shear force V2. M2 is equal to minus F1 multiplied by dx. So never forget that I just write the static equilibrium in calculating these internal shear force and bending moment. So this comes from sum of the forces has to be equal to 0, and sum of the moments has to be equal to 0. It is the same for V2 and M2. So M1 multiplied by X, and this has resultant of minus W X minus L. This is the resultant force, and it will act at the center, so it will act at point x minus L divided by 2. There will be a resultant here. So this distance is x minus L divided by 2. Therefore, this is square divided by 2. Okay. So these are the moments, in fact, and okay, so these are the moments. Now let's draw the moment diagram for this problem. So the moments are negative in general. As we see, the bending moments are negative. So I will draw the negative side. So this is my moment. Here is the positive side. So this is my point B, because this is where I put my origin. Then I have my point A, and this is my length L, so 2.5 meters. So in the first part, from A to the center, as you see, it is minus F1 multiplied by X. So it's linear. It increases like this from B to the center, and then I have this parabolic part. So the value here is minus F1 multiplied by L. So remember that L is 2.5 and F1 is 6 kilonewtons, so it is 15 Newton meters here. Kilonewton meters, sorry. Okay. Then from beginning from x equal to L, you have this parabolic contribution, and as a result it will increase parabolically, where here. So this is M1x and this is M2x. As we see from this graph, we see the maximum bending moment at point A. Therefore, we need to calculate the maximum stress at this point. So let's calculate the maximum moment. This is x equal to 2L. So M2 x equal to 2L is equal to minus F1 multiplied by 2L minus W. If you substitute 2L into x, this becomes the expression inside the parentheses will become L. So this is L squared minus L squared divided by 2. Just put the values. So this is minus F1 is 6 10 to the power 3, 2L is 5 minus 15 10 to the power 3. L square is square of 2.5, and So let me calculate the value. This is 6.25, square of 2.5 divided by 2. And from here, the value that we have is okay. It is let's have some precision. Okay, it is 76,875 Newton meters, and it's minus. So since we are asked for the maximum bending stress in the problem, we need to calculate the bending moment of inertia. Bending moment of inertia of the system is, in fact, I bending 1/12. So this is the bending moment of inertia with respect to the center. Since we have a square cross section, the neutral axis is just at the center. We don't need to calculate the centroid, and this is a to the power 4. So the bending moment of inertia for this system is 2.135 10 to the power 4 meter to the power 4. Now we can calculate the maximum, absolute maximum value of the stress. So remember that we have a square cross section, and certainly we see the maximum stress, maximum absolute stress on the surface of the beam, either here or here, and this distance is A divided by 2. Therefore we can write it like this: maximum bending moment divided by A divided by 2 divided by bending moment of inertia. This is the maximum stress. Value for the absolute value for the maximum stress is 7,875. A divided by 2 is 0.1125, so 1,125, and divided by 2.135, multiplied by 10 to the power 4. So let's look at the value for this. So the value for the maximum stress is 40.494 megapascals. So this is the maximum stress. Okay, our problem is 693. The wing spar ABD of a light plane is made from 2014 T6 aluminum and has a cross-sectional area of 800 mm square, a depth of 75 mm, and a moment of inertia about its neutral axis of 1.11 10 to the power minus 6 meter to the power 4. Determine the absolute maximum bending stress in the spar if the anticipated loading is to be as shown. Assume A, B, and C are pins. Connection is made along the central longitudinal axis of the spar. Okay, so we have a wing, and this wing is subjected to a lifting force as given in the figure. So this wing is connected to the plane with a pin at point A, and there is a support CB. So we have a thrust element, and as we see from the figure, there is no force acting on it. Therefore, we can directly say that the CB member carries load only along its direction. So let's begin by drawing the free body diagram of the system first, and so we are given the also we are given the area, uh, 800 mm square, yes, and the depth of 75 millimeters. Okay, so the distance to the surface is 75 millimeters. Distance of this structural member to the surface of the wing is given as 75 millimeters, and its moment of inertia, bending moment of inertia, is also given. Okay, so let's see how we are going to handle this problem. First, we will begin by drawing the free body diagram of the system, and then we need to draw the moment, bending moment around bending moment diagram. Okay, so this is our wing. Then we have the lifting force acting on it. Okay. Then we have a force FB acting along the thrust element, certainly we have a reaction force at A. So if we choose the coordinate system, like this, so we have x coordinate in this direction and y coordinate. So x is horizontal and y is perpendicular. Okay, so these are the forces. Certainly we have Fay and Fax, because we have pin connection and there is no reaction moment at point A. So okay, so this is the problem that we have. In fact, W is already given to us. The maximum value of this distributed load is given, that is 100 Newton per meters. Okay, and so we have bending moment of inertia that is given. IB is equal to 1.11 10 to the power minus 6 meter to the power 4. The depth of the neutral axis is given. It is 75 millimeters, so it is 0.075 meters. And area, cross-sectional area, is given. That is A is equal to 8 10 to the power minus 4 meters square. Okay, so first thing that we need to do is to calculate the forces, reaction forces, Fb, Fay, and Fax. In fact, it is more than enough if I calculate the Fb. Certainly, but what I'm going to do is I will decouple this force Fb into two. So let's say that I have Fby and Fbx. So I have two components of the force in x and y direction. In fact, it is more than enough if I calculate the y components, because the x components will not contribute to the bending moment and therefore will not contribute to the bending stresses. So I can neglect it at the moment, because we are asked for the maximum bending stress. Okay, now let's, from the static equilibrium, sum of the forces has to be equal to 0 and sum of the moments has to be equal to 0. In fact, for this problem it is much easier for me to use this rule. So sum of the moments with respect to any point has to be equal to 0, and I can take the moment with respect to A. Therefore I can eliminate the variables at point A, and since only the vertical component will contribute to the moment, I can easily calculate the EBY, FBY, and from there on I can calculate the I can find the bending moment diagram. So let's calculate the moment with respect to point A then. It is simple. So this is first, I can choose any direction. So sum of the moment with respect to A has to be equal to 0. So I choose the counterclockwise direction as positive in order to calculate the moment. And then, so the resultant force of this distributed load is well, let's define the variables. So I forget to do that. So I have two lengths. Let's say that this is L1, and then I have another length here, L2, then L1 is equal to 0.9 and L2 is equal to 1.8 meters. Okay, now if I write the sum of the moments, so that is W multiplied by L1 plus L2 divided by 2. This is the resultant magnitude of the resultant force, then multiplied by L1 plus L2 divided by 3. So this is the moment arm. So this, the resultant moment is somewhere here, sorry, in this direction. So this is the resultant force, Fr, and this is the moment arm. Let's say that X bar. Okay, this is the moment generated by this distributed load. Then I have the moment generated by Fby. Certainly this is Fby multiplied by L1. From here I can calculate the Fby. Fby is equal to W L1 plus L2 square divided by 6. And then that will be divided by L1. And of course it is negative. So if you put the values, W is minus 100, L1 plus L2 is equal to 2.7 square divided by 6 divided by L1 is equal to 0.9. So from here what we are going to find for the Fby is, so let's do the calculation. This is 100, 2.7 square divided by 6 divided by 0.9. It is 135 minus newtons. This is the value for the Fby. Okay, now we find the horizontal component, vertical component of force at B. So we don't need to calculate the horizontal component for this problem. Then next is to draw the bending moment diagram. Of course, first I will cut the structure between B and free end. Then I will make a second cut between A and B in order to draw the moment diagram. So this is my first cut. I have M1, I have the shear force, so V1 is equal to, here the magnitude is or let's say that this is W bar X, and W bar X is equal to W divided by L1 plus L2 multiplied by X. So V1 is equal to W L1 plus L2 multiplied by X and multiplied by X divided by 2. So the height divided by 2, it's the area under the triangle, or in other words we can easily write it like this. It is W X square divided by 2 L1 plus L2. Okay, now let's calculate the bending moment. M1, you can integrate it. This is one way of calculating this bending moment diagram, or you can directly calculate the bending moment generated by this resultant force. So this is the resultant force that is generated. So M1 is equal to we have the resultant force here, so it is Wx square 2 L1 L2 multiplied by this distance is X. So I put my reference to the right hand side for this calculation. So X divided by 3. From here you can find the bending moment in the first region, W X cube, divided by 6 L1 plus L2. So this is the first expression for the bending moment distribution. I can do the second one. So let's make a cut between point A and B. Again, I will omit the X horizontal component of the force at point B. It will not contribute to the moment. I will have only FBY. So I have V2, I have M2, and now again I put my reference to the free end. Therefore m2 is equal to w x cube. It will be identical to this one, divided by 6 L1 plus L2. This will be the moment, but now I need to add the contribution coming from the FBY. I choose the direction of FBY in the positive vertical direction, so this is plus FBY multiplied by this distance, because I take the moment with respect to the cut always. So this distance is x minus L2. And remember that the value for the FBY is 0. Now, this expression tells me something. If you draw the moment diagram for this problem, so let's draw the moment diagram in this case. So this is my moment. I have here my point B and I have here my point A. Let's say that in the first part my moment will increase with the cube of x. So it will sharply increase like this until point B. Then the contribution of FBY begin to act. Then it will decrease to 0 at point A. So this is basically m1 x, and this is basically m2 x. In fact, I see the maximum moment certainly at point B. This is where I will see the maximum bending moment. If you draw this function. Okay, so okay, so this is m1x again. So until B, m1x will act again, and from B the contribution of the FBY begin to get into the play. And remember that the value for the FBY is negative, so it will decrease, and at point A it decreases to it will become 0. Okay, so this is the bending moment diagram for us. So let's calculate the maximum value. The moment here. So this is basically m1 x equal to L2. So let's calculate the maximum moment. The maximum moment is bending moment is m1 x equal to L2, and that's equal to W L2 cube divided by 6 L1 plus L2. W is 100, L2 is 1.8 cube divided by 6 divided by 0.9 plus 1.8. So let's do the calculation. I will hold you for a second. Okay, so the bending moment is 36 Newton meters. Now we know the bending moment. Now next thing is to calculate the maximum stress. So this is M max multiplied by Y max divided by I bending so M max is 36, Y max is 0.075, and the bending moment is 1.11 10 to the power minus 6, and the value that you are going to find is let me calculate it. 1.11 2.432 megapascals. This will be the value for the maximum stress. Okay, so our question is 6/100. If D is equal to 450 millimeters, determine the absolute maximum bending stress in the overhanging beam. So let's look at the problem. We are asked for the maximum bending stress. In order to find the maximum bending stress, we have to find the location of the maximum bending moment. So as a result, we have to draw the bending moment distribution. So D is given. D is the height of the cross section. We have a hollow rectangular cross section. Beam is simply supported at point A, and there is a slider at point B. We have a distributed load between A and B, and in fact we have a point load of 12 kilonewtons at the free end. Point A will not support any moment, therefore we have only two reaction forces at point A. One is horizontal and the other one is vertical, and at point B we have only one support reaction, so that is vertical. So let's draw the free body diagram of the system. This is our beam. This this is our distributed load. It's a uniform distributed load. Its magnitude is W. We have a force here. At point B, we have only one reaction force in vertical direction, and at point A we have two support reactions. One is, let's say, vertical, or let's show it like this, vertical, and the other one is like this, FA, horizontal. So we have two force components. Okay, so this is our free body diagram, and let's say that this is F. Now we need to draw the moment distribution, bending moment distribution. In order to do that, we have to find the support reactions. In fact, we just need to calculate the support reaction at point B, and then we can begin to cut the structure from right hand side. Therefore, what I'm going to do is I will take the moment with respect to point A. But before that, first let us define the lengths. I will define some variables. So let's say that this distance is L1. In fact, this distance is L2, and as a result, L1 is equal to 4 meters and L2 is equal to 2 meters. So this is the moment distribution. Okay, and so let's write the W as well. W is equal to 8 kilonewtons per meter, and F is equal to 12 kilonewtons. Okay, so next I will take the moment with respect to point A. So this is what I'm going to do, and sum of the points, the moments with respect to any point has to be equal to 0. I will not write the sum of the force equilibrium for this configuration, because I don't need to calculate the reaction forces at point A. So sum of the moments with respect to point A is equal to 0. So let me write the moments. I can choose any direction as positive, doesn't matter. So let me choose the clockwise direction as positive. So this is equal to F multiplied by L1 plus L2. Then the moment of FB minus FB multiplied by L1. Then moment of this distributed load. The resultant force of this distributed load is W multiplied by L1. Certainly the resultant force will be at its geometric center of this area. Therefore it is L1 divided by 2. And finally I will have this expression. So this is my force equilibrium. From here I can calculate the FB. So FB is equal to F multiplied by L1 plus L2 plus W L1 square divided by 2 divided by L1. If you put the values into their places, F is equal to 12 10 to the power 3, L1 is equal to 4, L2 is equal to 2, plus W is 8 10 to the power 3, L1 is equal to 4 square divided by 2, and I will divide the whole expression with 4. So from here we can calculate the FB. So let's calculate the FB. So FB is equal to 12 10 to the power 3 4 plus 2 plus 8 10 to the power 3 4 square divided by 2, then I will divide the whole expression with 4. So it is 34 kilonewtons. This is the value for the FB. Okay, now I find the FB. Now I can I will make the cuts in order to determine the bending moments. So internal moments and forces. As I said, I will begin to cut the structure from right hand side. So first I will make the cut between B and this free end. So from here, then I will make the second cut from here. As a result, I have my force, I have my shear force, and I have my bending moment. So this is my X. For this piece I will write the static equilibrium. Obviously from here I can find the M1, and so I will take the moment with respect to the cut. So with respect to this point has a moment arm of X. Therefore I can easily say that M1 is equal to minus F multiplied by X, because this piece has to be in static equilibrium in any case, and therefore sum of the moments has to be equal to 0. M1, so moment applied to the here plus moment generated by this force has to be equal to 0 when you take the moment with respect to this point. And obviously you can write the V1 is equal to minus F. you can easily see it. So this is sum of the moments has to be equal to 0, and sum of the forces has to be equal to 0. So this is my first cut. Now I will make a second cut. So I will make the second cut between A and B. So somewhere here at an arbitrary location. Now this is my distributed load. I have my point load. I have my bending moment, and I have my shear force. Again, I will take the moment with respect to this point, with respect to the cut, in order to suppress the effect of shear force, because V2 will not generate any moment at this point. So M2 is equal to minus F multiplied by X. Now this length is X minus L2. So the moment generated by this distributed load is W X minus L2 square divided by 2. Okay, so well, I forgot something. I have FB here. That's okay. So I have the contribution of FB as well. So FB will generate a positive moment. So FB multiplied by X minus L2. So this is my so I find the moment distribution as a function of the coordinate. So here first M1, so it is minus Fx, and then it is M2. So let's draw the moment distribution, the graph. My moment is the road. This is my free end. This is my point B, and then I have the A here. So first, in the first part up to B, it will increase linearly. To a value which is minus F multiplied by L2, and then it will try to increase parabolically because of this turn. So when it is L2, this is 0. When it is L2 plus L1, this becomes L1. So this is the minus L1 square divided by 2. But FB will compensate it. As a result, at point A, it will decrease to 0. So it's going to be something like this. And it will become 0 at point A. So certainly this is the maximum. This is the location where we see the maximum bending moment. This is minus F multiplied by L2. So F is equal to it was 12 as far as I remember. Yes, it is 12 kilonewtons, and L2 is 2. So this is the value here is minus 24 kilonewton meters. So we look at the problem by means of absolute value because we are asked for the maximum stress. So negative sign means that just to determine which side is under compression and which side is under tension. So next thing is to calculate the bending moment of inertia for this cross section. So now let's draw the cross section. This is the next thing that we are going to do. So this is our cross section, and we are given that this is length D, and let's say that this is T, this is, let's say, B, or let's say that this is T1, and we have another one here, this is T2. In fact, the cross section is symmetric, therefore we don't need to calculate the centroid of this cross section, because it is directly located at the center because of the symmetry. So let's say that B is equal to 0.125 meters, T is equal to 0.025, or T1, sorry, T2 is equal to 0.075, and D is given as 0.45 meters. Now we will calculate the bending moment of inertia with respect to the center. In fact, it's hollow, so what we are going to do is, first we will think that we will consider that whole cross section is filled, and we will calculate the bending moment of inertia of this filled part. So this is 1/12 the width is B plus 2T1 multiplied by the, oh sorry, this is not D, D is this distance, huh? The total height is D. Anyway, given in the problem, that's, yes. Okay, so B plus 2T1 multiplied by the cube of the height. This is what we have. And then we will subtract the bending moment of inertia with respect to this axis, to the center axis. We will subtract the bending moment of inertia of this hollow region with respect to this the centroid. Axis passes through the centroid. So this is minus 1 over 12. This empty area has a width of b, and then this height is d minus 2t1, because we have 1t1 here, 1t1 here, and the cube of it. So I will use Mathematica for this purpose. So it is 1 over 12. B is 0.125 meters multiplied by B plus, this is the width, B plus 2t1, B plus 2t1, B is 0.125, T1 is equal to 25 millimeters, so it is 2 times 0.025 multiplied by d cube. D is 0.45, cube of it, plus 1 over 12. B is again 0.125. Oh, this is negative, by the way. Multiplied by D is 0.45 minus 2t2. Not T1, it has to be T2. 2t2, T2 is 0.025. .075, and the cube of it. So the bending moment is .047 10 to the power minus 3 meter to the power 4. This is our bending moment. Now we can calculate the maximum stress for this configuration. So sigma max, absolute value of the maximum stress is M max. Perhaps we will see the maximum stress on at the free surfaces, either here or here. So the distance to the surface is d divided by 2. Divided by the bending moment of inertia. Let's put the values. M max is equal to 24 10 to the power 3. D is 0.45 divided by 2. and then the bending moment is 1.047 10 to the power minus 3. Let's calculate the value for the maximum stress. So the maximum, this was the bending moment, maximum value of the bending moment is 24 kilonewton meters. So 24 newton meters multiplied by 0.45 divided by 2, and we will divide it to the bending moment of inertia, and then we obtain the value. It is 5.154 megapascals. So sigma max equal to 5.154 megapascals. So this is the result. This is the maximum stress. It can be compressive or it can be tension, but this is the maximum stress. Okay, our next problem is 6.103. Question is like this: if the overhanging beam is made of wood having the allowable tensile and compressive stresses of 4 megapascals and 5 megapascals, determine the maximum concentrated force P that can be applied at the free end. So we are given the allowable tensile and compressive stress, and we are asked for the magnitude of the force P which can be applied to the beam. So the beam is simply supported at point A. There is a slider at point B. The cross section of the beam is given. It's a P-like cross section, and in fact, first thing that we need to do is to find the support reactions by means of applied force P. In order to do that, in fact, we need to draw the free body diagram of the beam. This is what we are going to do first. So let's draw the free body diagram. Okay, this is our beam. We have a concentrated force of P. We have only vertical reaction at point B. We have both vertical and horizontal reactions at point A. In fact, point A is pinned, therefore we don't have any moment, reaction moment at point A. So we will calculate, we will take the moment with respect to point A. So sum of the moments with respect to any point has to be equal to 0. In fact, by taking the moment with respect to point A, we'll eliminate the effect of forces at point A. Therefore, we left with only the force at point B as an unknown. So let's define the lengths. So from A to B, let's say that this is L1, and from B to the P it is L2. L1 is given as 2 meters, L2 is given as 1 meter, and so let's write the moment. We can take any direction as positive, so let's say that the clockwise direction is positive, therefore P multiplied by L1 plus L2 minus FB multiplied by L1 is equal to 0. From here, FB can be calculated as P multiplied by L1 plus L2 divided by L1. Okay, so this is the value for the FB. Now what we are going to do next is to draw the moment distribution. So we will make two cuts. First, I will take the right hand side as reference, so I will make the first cut between B and the free end, then I will make the second cut between A and B. So this is P, this is V1, this is M1. I take the direction of the moment here, so I just will write, I will take the moment with respect to this point, and then I will eliminate the effect of shear force. So M1 is equal to minus P multiplied by X. In fact, V1 is equal to minus P. So this is sum of the forces equal, sum of the moments has to be equal to 0, and sum of the forces has to be equal to 0. This is the static equilibrium condition in that. Okay, so this is the first cut. Now I will make the second cut. So I have my P here, I have my FB here, I have V2, I have M2 here. So again I will write this static equilibrium, sum of the forces has to be equal to 0. This basically gives me that V2 is equal to FB minus P. I can put the FB into its place. FB is equal to P L1 plus L2 divided by L1 minus P. So from here I can find the V2 as P times L2 divided by L1. Let me calculate the moment. I will take the moment with respect to the cut to point here. So it is minus P multiplied by X minus, plus FB multiplied by X minus L2. So let's write the M2 here in an open form. It is minus P multiplied by X. FB is equal to P multiplied by L1 plus L2 divided by L1 multiplied by x minus L2. So this is the expression for bending moment in the second region. Now what we are going to do is to draw the moment distribution in order to see how it changes. So this is x, this is our point B, and this is our point A. So this is the moment. Now in the first region, M1 is acting, and M1 is it is minus P multiplied by X. It is something like this, and then it will tend to decrease. So when X is equal to L1 plus L2, this expression will vanish. Okay, so now as a result, the moment at point A is 0, and therefore we can easily see that we see the maximum moment, bending moment, at point B from this graph, because this is M2 X and this is M1 X. So we can easily say that maximum is at M1 X equal to L2. So it is minus P multiplied by L2. Sorry, this is the absolute value, and let's take it plus, because we are interested in the the compressive and okay, so we will not take the absolute value, it's negative. We will consider the direction as well, the sign of the moment also. So this is negative. Let's write it again here. So this is M1 X equal to L2, and that's equal to minus P multiplied by L2. That's okay. Now this is the maximum bending moment. This is the critical point for our design. So next is to determine the bending moment of inertia of the cross section. Now we have a P-like cross section. And certainly we have the neutral axis somewhere. We don't know the location of the neutral axis. So the first thing that we need to do is to determine or calculate the location of the neutral axis. As a result, we will calculate the centroid. I need a reference point. In fact, I prefer to choose the bottom of the cross section as my reference. Now let's define the dimensions and by means of some variables. So let's say that this is t. In fact, cross section is symmetric with respect to the vertical axis, so this is t as well. This is t as well. Let's say that this is b. This distance is b, and this is height. Let's say h. So t is 0.025 meters. B is given as 0.15 and h is given as 0.2. Okay, so this is the these are the dimensions of the cross section. Now let's calculate the centroid of this cross section. Y bar. This distance is y bar. So y bar is equal to sum of the moments of the areas divided by sum of the areas, so total area. Now we have three areas. As we see, three regions. Therefore, first I will, since the cross section is vertically symmetric, I will begin from these two areas. So multiply it by 2. Their geometric center is located at h divided by 2, or let's h multiplied by t is their area, and their geometric center is located at h divided by 2, plus this area, this is b multiplied by t, and its geometric center is located at h plus t divided by 2, and the total area is 2h multiplied by t plus b multiplied by t. This is the total area. This will give me the geometric center of the area. So let's calculate the value. So it is 2 h is 0.2 multiplied by t 0.025 multiplied by h divided by 2. H is 0.2 this is the moment of the areas which are vertical, and then B, that is 0.15 multiplied by 0.025 multiplied by H is 0.2 plus 0.025 divided by 2. These are the moments of the areas. And then I will calculate the total area. This is 2 multiplied by 0.2 multiplied by 0.025 plus 0.15 multiplied by 0.025. So this is the location for the natural axis. It is 0.130 meters. Y bar is located here. So now what we are going to do is to calculate the moment of inertia, the bending moment of inertia. So again, we will write the bending moment of inertia for this cross section. Now first I will calculate the bending moment of inertia of these two areas, and then I will calculate the bending moment of inertia of this area with respect to the neutral axis. So first I will calculate the bending moment of inertia of these areas with respect to their centroids, and then I will shift it to the neutral axis. Since I have two areas, I have 2 1/12 T multiplied by H cube plus area of this region, that is T H multiplied by T, and the distances between the neutral axis and its centroid, so square of it, so it is H divided by 2 minus Y bar square. Plus, now I will calculate the bending moment of inertia of the, okay, so the moment of inertia of the area which is horizontally aligned at the top of the cross section is this area. With respect to its centroid is 1/12 B T cube. Then we will shift it to the centroid of the cross section, plus area is the B multiplied by T. Its centroid is located at H plus T divided by 2, so distance to our reference point, minus y bar and square of it. So this is the expression for bending moment of inertia. Okay, so let's calculate the values. I will use Mathematica for this. IB is equal to, so 2 multiplied by 1 over 12 TH cube. T is 0.025, H is 0.2, cube of it, plus 0.2 multiplied by 0.025. This is the area, and distance between the centroids, that is h divided by 2, 0.2 divided by 2 minus y bar. This is the moment of inertia of the areas which are vertically aligned. Now the area at the top, it is 1 over 12, B is 0.15, T cube, that is 0.025, plus, now we will shift it to the centroid, that is the area of 0.15 multiplied by 0.025 multiplied by h, that is 0.2, plus t over 2, that is 0.025 divided by 2 minus y bar square. So we find the bending moment of inertia. Bending moment of inertia, therefore, is 6.804 10 to the power minus 5 meter to the power 4. Okay, now we calculated the value. We have just calculated the value for the bending moment of inertia, and now next thing is to calculate the stress. Now let's go back and look at the value for the maximum stress. Remember that we see the maximum stress at point B. So we see the maximum stress at point B. In fact, this is therefore the stress there is P multiplied by moment there is minus P multiplied by L2 so next we will we will calculate the maximum value for the P. We will calculate two different values. Now we have determined the value for the cross section. In fact, we find that maximum moment was minus P multiplied by L2. So remember that. So we choose the direction of M1 in this direction, and we find that it is negative. So we can easily say that the moment is in this direction, therefore we can easily say that the bottom of the cross section will be subjected to the compression, and the top of the cross section or top of the beam will be subjected to tension. So therefore we can easily say that we have tension here and we have compression here. Now we will calculate the maximum values for the tension and compression. So remember that the stress is equal to minus M Y divided by I bending. Here Y is the distance to the, or let's say Y prime, that's better in order to differ it from our coordinate system. It is the distance to the centroid. Now we will substitute the value for the moment. So moment is equal to minus P multiplied by L2. So this is minus P L2 divided by I bending multiplied by Y prime. So we are given the allowable stresses for tension and compression. For tension it is, so let's write it here, sigma T allowable is equal to 4 megapascals, and for compression it is 5 megapascal. Okay, so we have 5 megapascal and 4 megapascal stresses in fact. So let's calculate the value of the P. Now I will omit the negative sign here because I know where the tension and compression occurs. So remember that this is the tension. So I will calculate the distance of this point to the centroid. In fact, that is, let's say that Y prime tension is equal to H plus T minus Y bar, and Y prime compression is equal to Y bar directly. So these are the parameters that we have. Now we will I will substitute these two values into this expression, and I will omit the negative sign because I will use the absolute values. So from this equation for the stress and moment, I can easily calculate. I can say that P is equal to sigma multiplied by I bending divided by L2 Y prime. So from here I can calculate two values. For the tensile, it is PT. For the tensile load, this is 4 10 to the power 6. I bending is 6.804 804 10 to the power minus 5 divided by L2. Value for the L2 is 1 meter, and then it is YT, so it is H plus T minus Y bar. H plus T is equal to 0.225 minus Y bar, and Y bar is equal to 0.13. Okay, if we let's make the calculation. So it is 4 10 to the power 6 multiplied by I bending divided by 1 multiplied by 0.225 minus the location of the centroid. So from here we find the value 2885.79 newtons, but we need to calculate the compressive one as well. So the compressive one is again sigma compression. So the compression for the compression allowable stress is 5 megapascals. So that is 5 10 to the power 6 multiplied by 6.804 10 to the power minus 5 divided by 1, so it is L2. Now location of the compressive stress, maximum compressive stress is at has a distance of y bar to the centroid, so it is 0.13. And let's calculate it. So it is 10 to the power 6 multiplied by I bending divided by 0.13. So 1 multiplied by 0.13, or let's say y bar directly. So it is 2603.49 newtons. As we see, therefore we can easily say that the maximum force that can be applied to this beam is 2603.49 newtons. So this is the answer of the question. Okay, our question is 6-109. The box beam is subjected to the internal moment of 4 kilonewton per 4 kilonewton meter, which is directed as shown. Determine the maximum bending stress developed in the beam and the orientation of the neutral axis. Now, we have a moment, and we know that the moment is a vector quantity. In fact, we have a box, so rectangular cross section, which is hollow inside, and the direction of the moment is given. So until now we have seen how to handle the problems which has bending moment only around one axis, and commonly that is the z axis. So this is what we have seen. Now we will analyze this problem. We will solve this problem, in fact. So let's have a look. First, let us draw our cross section. Now, as we see, the cross section is symmetric with respect to the x and y and z axis. So therefore, this is our y axis and this is our z axis, and in fact moment is a vector quantity, and given in this direction it makes an angle theta. Now we have seen how to handle a problem when the moment is positive, and in fact how to handle only one moment, and possibly that moment is in the direction of mz. In case of an mz, we know that the stress is equal to minus mz. Mz is the bending moment which generates bending, and y is the distance from the centroid divided by bending moment of inertia around z axis. So this is the case. Now let's see, we have another moment in fact, and perhaps let's assume that the moment is positive. So we have my. Of course, this my, so here we see that when y is positive, the stress is negative, even though mz is positive, and therefore we have a compressive stress, and compressive stress is in fact, generally we assume that it is negative. Now let's assume that we have a moment my, and according to the right hand rule, we will see that this point, so negative z, will be compressive. So z is negative divided by bending moment of inertia with respect to y-axis, and since the stress is additive, so we are talking about a linear problem, and we are generating a stress along the beam, so the normal stress, we have a positive sign here. So this is the general formula for an arbitrary loading, so when you have bending in more than one axis. So this is the fundamental formula. Okay, in fact what you should do is, if the cross section is not symmetric, you should calculate the location of the centroid with respect to both directions, and you should locate it. Now let's calculate first the maximum stress. In order to do that, we need to calculate the bending moment of inertia around z-axis and around y-axis. So this is what we should do. Now let's define some variables. Okay, so we have here B, and let's say that we have T here. This dimension is T, and we have H. So let's say that this distance, this dimension is H. So as a result, H is .15 meters. T is equal to 25 millimeters. So it is 0.025 meters. then we have B. B is equal to 0.1. Let's say that this is T1 because we have another thickness here, so this distance is T2, and T2 is equal to 0.05 meters. Additionally, we have the angle theta, and theta is given as 45 degrees. Now these are the variables. So we define the variables. Now let's calculate the first. We need to calculate the moments my and mz, because moment is a vectorial quantity, and iz and iy. So iy and iz are the bending moment of inertia around z-axis and bending moment of inertia around y-axis, since it is the centroid. It will the structure rotates around this axis. This cross section will tend to. Okay, so let's calculate the moment first. Therefore we can write the moment like this. Moment is equal to m, so m is given to us, multiplied by minus m multiplied by sine theta j vector plus m cosine theta k vector. Or in other words, we can write my is equal to minus m sine theta, and mz is equal to m cosine theta. So now we know the moments. Let's calculate the bending moment of inertia around y and z axis. For this purpose, what I'm going to do is, first I will calculate the total bending moment of inertia of the field region around, for example, for iz around z axis. Then I will subtract the bending moment of inertia of this hollow region. So let's calculate the iz. Iz is equal to 1/12 the width. Width is equal to b plus 2t1 multiplied by the total height of the cross section, and that is 2h cube. So it is, this total height is b plus t1 plus t1, and the total height is h plus h, 2h, minus 1/12. Now it is the bending moment of inertia of this hollow region, and this hollow region has a width of b multiplied by 2h minus 2 T2. Cube. This is the bending moment of inertia for IZ. So we can calculate it. I will do it by using Mathematica. Okay, so it is let's change the screen. So it is 1/12 multiplied by B. B is 0.1 plus 2 T1. T1 is 0.025 cube. So this is the moment of inertia of the total area. Now I will subtract the moment of inertia of the hollow region. It is minus sorry, this is wrong. It's it is the 2h, and h is equal to 0.15. Okay, minus 1/12 multiplied by B. B is equal to 0.1 multiplied by 2 times 0.15 minus 2 times 0.05, that is T2, and the cube of it. This is IZ, and the value we have is for IZ, it is 2.708 10 to the power minus 4 meter to the power 4. So this is IZ. Now let me calculate the bending moment of inertia around y-axis. So again I will calculate the bending moment of inertia around y-axis. So therefore now the height of the rectangle is this region. So it is 1/12 multiplied by the edge length of the base. So that is 2h multiplied by the cube of the height. So that is B plus 2T1 cube. Now I will subtract the moment of inertia of this hollow region. So it is minus 1/12. Now the edge length of the base is 2h minus 2t2, and the height is b cube. Now again I will calculate it by using Mathematica. So it is 1 over 12 multiplied by 2h, h is 0.15, and multiplied by the cube of the height, that is b plus 2t1. t1 is 0.025, and the cube of it minus 1 over 12 2 times h is 0.15 minus 2 times t2 is 0.05, and the height is 0.1, and that's the cube of it. So the result is 6.77 10 to the power minus 5. Meter to the power 4. Now we find the bending moment of inertia in both axes. So we are asked for the maximum stress. Certainly and possibly we will see the maximum stress where y values are at the extremes, so possibly either here or here or here or here, and in fact the structure is symmetric, and we will so that's the farthest point. So let's calculate the moments in y and z axis respectively. So if we analyze the problem, carefully, we will see that we will see the maximum stress at a point where both moments creates a compressive stress, and where both moments creates a tension. So this is for this problem my. So according to the right hand rule, my will generate a compressive stress here and tensile stress on this surface, whereas the mz will generate a compressive stress here and tensile stress on this surface. So as a result, I can easily say that I will see the maximum stress by means of absolute value either at this point or at this point. Since the cross section is symmetric, the absolute value of the stress at this point and at this point will be both points has to be the same. So I calculate the moment of inertia. I can choose either location. In fact, I will choose this point. So here both y and z axis are positive, and as a result I can say that y max is equal to h and z max. So these are the coordinates of the point where I am going, where I will see the maximum stress, is equal to b plus T1. So we see that sigma max is equal to absolute value minus my multiplied by y divided by this is mz iz plus my multiplied by y multiplied by z divided by iy, and the absolute value of it. So this is equal to so this is my stress. So mz multiplied by y divided by iz plus my multiplied by z divided by iy. So this is minus. So remember that mz is equal to m multiplied by cosine theta multiplied by, so these are the maximum, these are the maximum, we can put y max, so this is h divided by iz, my is negative, so this is minus m multiplied by sine theta multiplied by z max. Z max is equal to b plus T1 divided by iy. So m is given in the problem already. So m is given as 4 kilonewton meters. So let's put the values into their places. I will omit the negative sign because I have the absolute value. So this is 4 10 to the power 3 cosine 45 multiplied by h. H is equal to 0.15 divided by iz. Iz is equal to 2.70, 8 10 to the power minus 4 plus 4 10 to the power 3 multiplied by sine 45 multiplied by b plus T1, b, sorry, this is b divided by 2, by the way. It's not, so it is the distance, b divided by 2. So this is b divided by 2 plus T1, b is 0. B divided by 2 is, b is 0.01, and T1 is equal to 0.025 and divided by iz, that is 6.77 10 to the power minus 5. So let me write it again in order to have make it clean. So let's say that, so sigma is equal to 4 10 to the power 3 multiplied by cosine 45 multiplied by 0.15, that is h, divided by 2.708 10 to the power minus 4 plus 4 10 to the power 3 multiplied by sine 45 multiplied by b divided by 2. b divided by 2 is 0.05. t1 is 0.25 divided by moment of inertia, that is 6.77 10 to the power minus 5. So this is our expression for the stress. Now let's calculate it with Mathematica. So m is 4 10 to the power 3 multiplied by cosine 45. Cosine 45 is equal to p divided by 4 multiplied by 0.15 divided by Iz plus 4 10 to the power 3 multiplied by sine p divided by 4 multiplied by 0.05 plus 0.025, and we will divide it by moment of inertia around y-axis, so Iy. As a result, we find the maximum stress as 4.7 megapascals. Okay, now we are asked for the angle for the orientation of the neutral axis. Certainly we know that it passes from the geometric center, but what is the orientation for it? Now let's write the stress formula again. Sigma is equal to minus mz multiplied by y divided by Iz plus my multiplied by z divided by Iy. Let's put the mz and my into their places. Therefore, from here, this is my is equal to, mz is equal to m cosine theta multiplied by y divided by Iz plus this is minus sine theta multiplied by z divided by iz. So this is the expression this is Iy, by the way. Okay, so this is the expression for stress, and we already said that by definition the neutral axis is the axis on which the stress is zero. So let's say that this is equal to 0. Since m is constant, they will cancel, and from here we will see that cosine theta multiplied by y divided by iz plus sine theta multiplied by z divided by iy is equal to 0. Now let's draw our axis again. So this is our cross section, and we are given the y in the vertical direction and z is towards the left hand side in the horizontal direction. Now we need to define an angle. So let's say that, let's take an arbitrary point which passes from the center. So and let's say that this is alpha. For this arbitrary point, tangent alpha is equal to y divided by z. So let's calculate the y divided by z from this expression. So we will put the I will rewrite this expression again to here. So I can easily write like this: cosine theta multiplied by y divided by iz is equal to minus sine theta z divided by iy. From here I can calculate the y divided by z. So y divided by z is equal to minus sine theta divided by cosine theta multiplied by iz divided by iy, or in other words it is minus tangent theta multiplied by iz divided by iy. I can calculate this value. So let's do the calculation. Let's put the values into their places. So theta is 45 degrees. It is p divided by 4 multiplied by iz divided by iy. So, and I have minus. In fact, this is the value. So we find that it is equal to 4. Now I can calculate minus 4, sorry. Now I can calculate the angle for this. So this is equal to arctangent minus 4 so this is in radians, so I will divide it to P and multiply it with 180 in order to convert it into the degrees. So it is minus 75.96 degrees. The alpha is. And that's equal to minus 75.964 degrees. So remember that we choose the direction alpha as positive, so the natural axis is oriented something like this.